So before we get started, I just want to remind you that your first homework assignment is now posted, right? So if you log on to your Atoc account, and I realize for those of you that joined the class late that I forgot to send out that new invitation, which I will do so right after class. If you don't see it, send me an email. So the assignment is here. So basically all of the questions are under this folder, say homework 1, and the due date is in the title of the folder. It's also on the on my courses. And so just be careful that you look to see what kind of questions it is. And so for instance, it'll tell you that for question 1 that multiple answers are possible. So if you want, in order to get that right, you would have to choose everything that applies. Okay? Now you'll notice there's a discussion topic up here that says homework 1 questions. So if you have any questions about homework assignment 1, you post them under this discussion topic, right? So you click on that and you write out your question. Now, everyone in the class will be able to see your question. They will not be able to see who asked it. Okay? So what happens is, and the reason we do that is that so people can see what other people are asking and we don't get the same question asked multiple times, right? So if you can see that a question has been asked and an answer has been given, and so what will happen is that if you want, you can actually respond with an answer to people. That's something that you can do. When me or the TAs respond, we will put who we are in our response, okay? So that you'll know the difference. Okay, but your posts are anonymous to each other. We can see who asked them, but you guys won't be able to, okay? And yeah, and that's basically it. And so you can re-answer questions as many times as you want. At 11:30 on the 26th, the assignment will close, and whatever answers you've submitted will be the answers that you have at that point. Okay? Now, a quick word. There is one question, which is question 10, which is a discussion question. It's a little more open-ended. It's something that we will grade manually. Okay? Now, for that one, try to have, write out your response separately outside of Top Hat, and then post it once you think you have your response down. Because the problem is that it actually logs every time you put it in without overriding what you had before. So like if you wrote a paragraph out and then you decided that that paragraph wasn't quite right, you can submit another paragraph, but then we will have both paragraphs as submitted answers from you. Okay? So normally in that case, we just take the final submission, but it makes our life easier if you just submit a discussion question answer once. We're not holding you to that. It just makes our life a little bit easier. All right. So, yeah, if you have any problems, of course, contact me or the TAs. But it should be pretty straightforward. These things have gone pretty smoothly in the past. Now, in terms of where we left off, we were basically talking about sort of the technical aspects of getting weather data. And we talked a bit about radars and how you can actually tell which direction the winds were blowing based on Doppler radars. So today we're going to pick up with wind profilers. And wind profilers are similar to Doppler radars, except they're tuned at a level where they're really designed to see the wind even if there is no precipitation. Okay? So it's essentially instruments that are tuned beyond even what we would consider to be clear air mode in a Doppler radar, right? Because we said that Doppler radars, you can actually tune the sensitivity based on whether there is precip, there isn't precip, or whether that precipitation is rain versus snow, because rain is actually more visible to the radar than snow is. So you can tune these things. And then we have specific instruments that are actually tuned to see the wind, and even without precipitation. And what it does is that it actually uses sort of like differences in the density of the air to help it track wind movements. And so what that allows us to do is actually infer the winds between, say, half a kilometer above the ground and about the top of the troposphere. And that can give us information where we don't have balloons, for instance, right? So this is a way of getting wind information throughout the atmosphere in areas where we don't launch weather balloons. Okay, and there's other ones that are essentially radio acoustic sounding systems, and this will actually not only track wind information, but it gives us temperature information. And the way it gives us temperature information is because, so anytime a wave travels between two mediums, like, so you know if you shine light from air into water, that light beam gets refracted, right? So it actually gets bent as it goes from air into water. Well, these beams also get refracted based on whether the air is cold or warm, because cold air is more dense and warm air is less dense. The change in density of the air due to the temperature actually causes the beam to deflect slightly. It's not anywhere near as much as the amount of deflection we get, for instance, going from air into water, but the slight differences in density actually causes the beams to deflect. And so we can also tell something about the temperature information by pointing these things vertically. And actually McGill has its own set of these instruments. Not only do we have our own radar, but we also have our own sort of wind profilers and radio acoustic instruments. They're actually sitting, well, the radar is out, not in the middle of downtown Montreal, because if it was in the middle of downtown Montreal, the buildings would block a significant portion of the beam. But the other instruments are actually just sitting on the roof of Burnside. And these are where most of these instruments are located. And you'll notice that, so you see Montreal's, So you see Montreal's instrument there. And the other thing that you'll notice is that, well, obviously in the Northeast Corridor and along the west coast of the United States, right, where a lot of people live, these instruments tend to be located. But you'll also notice that there's a pretty good array of them over the central plains of the United States, the central and southern plains of the United States. And that's because that's Tornado Alley. All right, that's by far the region of the world, and we'll talk about this when we actually talk about severe weather and thunderstorms and tornadoes. But that part of the world is by far the most active relative to tornadoes. In fact, something like 80% of all tornado reports around the world actually come from this region. And so these things are placed there in order to help us with that prediction. So now we're going to talk about something that maybe is a little bit more intuitive. We're going to talk about satellite pictures. And I think just about everybody's probably seen a satellite picture at one point or another, right? But there are different kinds of satellite pictures. And one of the first kinds that we're going to talk about is actually an infrared satellite image. Okay, so when we talk about an infrared versus a visible satellite image, basically what we're doing is we're talking about the kind of radiation that the satellite is actually measuring. So when we talk about a visible satellite image, we're actually capturing the visible light. When we're talking about an infrared satellite image, we're actually capturing the infrared radiation coming off of an object, which is a function of its temperature. So we're actually measuring the temperature of the cloud or the surface or whatever the satellite is looking at. It doesn't have to be a cloud. So on an infrared satellite picture, the regions that appear bright tend to be cold, and the regions that appear dark tend to be warm. Now, the way we represent hot and cold is arbitrary, right? So we assign the color. But the convention that we end up using is that bright represents cold and dark represents warm. Especially if we're looking at a black and white image. So areas that are dark tend to be clouds that are low to the ground or warm clouds, and we'll discuss this more in a second. And warm regions of the surface. So if you're looking at a non-snow covered surface, for instance, it'll appear dark on an infrared satellite image. Now, the relationship of sort of the temperature of the cloud and its height in the atmosphere is that the higher the cloud, the colder it is. And that's because simply the temperature of the atmosphere decreases as you go up in the troposphere. Okay? So since the temperature is decreasing as we go upwards, the temperature of the clouds that are higher tend to be lower. And so they will be cold. So if we see a cloud with a really cold temperature, we know that it is likely high above the surface. And that's all this figure is showing here, right? So it shows that as the top of the cloud goes up in altitude, the temperature decreases. Yeah, so what happens is that at the top of the troposphere, the temperatures are actually pretty similar around the world. So you can actually have, it's just that the troposphere in the tropics would be at, say, 15 kilometers, and the troposphere, the boundary between the troposphere and the stratosphere would be at 15 kilometers in the tropics, but it might be at 10 kilometers in the poles. So the temperature at 15 kilometers in the tropics would be about the same as the temperature at 10 kilometers in the poles. And so this might be what an image looks like. And here again, the color system is arbitrary, but you can actually see the temperatures here, and the coldest temperatures, which are in the order of -70 or -80 in these reds, are actually at the center here. So we know that, for instance, that area is the coldest part or the highest clouds. So we know that that is the portion of this cloud system that is highest up in the atmosphere. Now, visible satellite image essentially measures what we call albedo. It measures how much light is reflected off of a surface. So, for instance, on a visible satellite image, it might be difficult to tell between sort of a bright white cloud and snow cover. Right? So if you have fresh, deep snow cover and a bright cloud, those both have albedos that are pretty high, and so they reflect similar amounts of light. So it becomes difficult to tell. In general, the thicker the cloud, the more light it reflects. Okay, so in general, things on visible satellite images that look bright are thick clouds, or snow, or ice. Thinner clouds tend to be darker, and the darkest regions will be areas such like oceans and forests and water, bodies of water, because those actually reflect very little sunlight. And obviously, the visible satellite only works when it's daylight. All right, once the sun sets on any portion of the globe, the visible satellite image becomes useless. And that might seem trivial, but I actually remember being on a field project once where one of the people we were working with was complaining that the visible satellite was broken, even though it was like 1 a.m. Right? So there's no light to reflect. And so visible satellite images are only valuable during the day. So these are typical albedo values for different kinds of things, clouds up top, and then different things like snow and different land surfaces at the bottom here. And so you can see that, for instance, the Pacific Ocean only reflects about 7% of the sunlight that hits it. So on a visible satellite image, the Pacific Ocean would look very dark. And then as far as these clouds, essentially these clouds go from thick at the top to thin, right? So the clouds up top, the cumulonimbus is the type of clouds we would associate with a thunderstorm. It's a big, thick cloud, and it's really bright. And it is actually about as bright as fresh fallen snow. So you actually get different pieces of information by looking at the different satellite images. The infrared satellite images tell you more information about how high or low a cloud is in the atmosphere, whereas the visible satellite image tells you more information about how thick or thin the cloud is. All right, and so you usually have to look at both to actually get a complete idea of what's going on. So this is a developing thunderstorm on a visible satellite image. So this is the part of the cloud that is thickest, right? So that's the bright part, and then the cloud actually grows over time, and the area of the clouds that are thick becomes larger and larger and new thunderstorms start to develop. And then the areas surrounding it that aren't quite as bright are areas where the clouds are a bit thinner. And so, generally speaking, thick clouds are the ones that are associated with the most precipitation. The thicker the cloud, generally the more water content it has, and the heavier the precipitation rate associated with it. Right? So most of our weather, most of our really interesting weather is associated with clouds that are relatively thick. And then there's water vapor image, which again measures the water vapor content of the atmosphere. So it's measuring basically how much liquid is in the air, but it doesn't necessarily have to be where there are clouds, right? Because we can have water vapor in the air without the formation of clouds. Now, clouds will have a lot of water vapor associated with them as well. So clouds will tend to show up on a water vapor image, but there will be areas on a water vapor image that will appear white that may not actually have clouds present because it is water vapor but no clouds. So basically on a really humid day in the summer, for instance, it can be sunny, right? But there could still be a lot of water vapor in the air. And that would show up on a water vapor image. And this is a animation of a water vapor image. And if you look at what's going on over here, that's essentially a hurricane hitting the Gulf Coast of the United States. Okay, so obviously the hurricane is an intense area of water vapor, but you'll notice that there's water vapor everywhere. So there's water vapor throughout the Pacific here. These regions that are dark are regions where the atmosphere is relatively dry. Right? So the fact that you're over the ocean isn't enough necessarily to ensure that there's a lot of water vapor in the atmosphere. So we can actually look at some examples. Okay, so these are images from the same time, but of different types of satellite images. So the first one up here is a visible image. And so when we look at the visible image, again, the thicker clouds are essentially areas that are brighter. And so there's a lot of cloud cover here, right? We notice that there's cloud cover basically all up and down the eastern seaboard of the United States, stretching into Quebec and Ontario, a very solid deck of clouds throughout the upper Midwest, and even some clouds out over the Pacific. Now we're going to compare that to the infrared satellite image to actually get an idea of which of these clouds is actually higher versus lower up in the atmosphere. So when we click on the infrared image, we start to see a little bit more detail. You notice that parts of this cloud shield are very bright. So these areas that are both bright on the visible and infrared satellite image would indicate that the clouds are both thick and extend to high up in the atmosphere, which likely means that the amount of precipitation falling from them is large. We'll notice that the clouds out here in the Midwest aren't as bright, So they're actually lower in the atmosphere. They don't reach quite as high. And these types of clouds would tend to be more associated with light precipitation or no precipitation at all. And then we can check the water vapor image all at the same time. And so you'll notice that you get a pretty good idea of where it's dry versus where it's moist. But in general, the water vapor image is going to somewhat mimic the cloud image. So where there are clouds, there's definitely water vapor, but there can also be water vapor where there aren't clouds. And so we can also check as to what's happening right now, right? So this is a web page, and this is linked in your presentation. This is a web page where you can actually check current weather information. And so we're going to start with a visible satellite image. Montreal is sitting right here in a deck of clouds, and you notice that clouds are pretty ubiquitous, right, over southern Canada and parts of the United States. So this might suggest to us that it's not going to get sunny anytime soon. The cloud shield is actually quite large, and if you actually look at the forecast is for it to remain cloudy over the next 2 to 3 days. Now, we can compare that to the infrared image. And we notice that those clouds are not very visible at all on the infrared image. So the clouds that we're looking at, even though they're somewhat thick, they're actually relatively low to the ground. And so this is an indication that we're not actually getting much, even though we're expecting clouds, we're probably not expecting much in the way of precipitation, because the clouds don't extend high up into the atmosphere. So this is essentially low clouds, low but somewhat thick clouds. And so you kind of have to be a bit of a detective, right? You have to put together the little pieces of information that you're getting from the different satellite images to actually get a depiction of what's going on. So these are the different satellites around the globe. The ones that are listed as GOES, the ones that are listed as GOES are essentially geostationary. So the satellite is rotating with the Earth. It stays over the same position relative to the Earth all the time. The other ones, the Meteosat ones, actually orbit around the Earth, and so you don't have constant coverage. Another way that we actually get weather data is through airplanes. Like back in the day before everybody had their own personal entertainment system with them, whether through their tablets, laptops, or phones. You could actually, if on the screens, one of the things that you could watch was the temperature and wind information outside of the plane. Now, very few select people used to choose to watch that information, but I would occasionally, because I could tell what was happening with the weather, broadly speaking, by following the changes in the temperature and the wind. But the airplanes still record this information, and they report it back to the National Weather Services across the globe. Now, this is most useful near airports because planes descend and take off near airports, and so we actually get information about the vertical structure of the atmosphere, right? When planes are flying at a constant altitude, we're getting information, but it's only information at one particular level. But when the planes land and take off, that actually gives us information about the vertical structure of the atmosphere as well. So this type of data is most useful, generally speaking, around airports, excuse me, and around busy airports. So the last thing in terms of this type of data collection is a lightning detection network. And so I don't know if you've ever tried listening to the radio, for instance, on your car, and there happened to be a thunderstorm around. There would be these pulses of static. And these pulses of static are actually indications of lightning strikes because the electromagnetic field associated with the lightning bolt is actually disrupting the radio transmissions. And so we can actually measure the intensity and location of lightning strikes that hit the ground based on the disturbances that those lightning bolts create in the electromagnetic field. And especially if we can see a lightning strike, we basically need to see a lightning strike from 3 sensors to be able to pinpoint exactly where it is. And when we do this, the accuracy of this is on the order of a couple of meters. All right, so we can tell where the lightning bolt struck within meters. And if you actually go to the Environment Canada website, you can actually find where lightning is occurring in Canada. So you can actually click on a lightning image, and it'll show you where the lightning is and how long ago that lightning bolt hit. One of the curious things about lightning, though, is that we don't actually warn for lightning. So, for instance, if there's a thunderstorm and it has a lot of lightning activity, we won't put out a severe thunderstorm warning because there's a lot of lightning, even though lightning actually is responsible for a significant portion of deaths associated with thunderstorms. We don't actually warn for it. Good rules of thumb on lightning. We'll talk more about lightning safety when we talk about thunderstorms. But good rules of thumb is that if you can hear thunder, you're within range of being hit by a lightning bolt. Okay? And so this is a little more technical details, but this is basically FYI. If you feel, if this is the kind of thing that interests you, you can read through it. And we can get images like this, right? So each of these pips basically represents a lightning stroke, and how long ago they occurred is essentially color-coded. So both Canada and the United States have lightning detection networks. So are there any questions on radars or satellites or any of our instruments? All right. So I'm going to move on to weather maps. And this is a depiction of a weather map. Some of you might have seen something like this before on the local news, or if you ever watched like the Weather Network or anything like that, you've seen depictions like this. So we're going to go more into this as we go along, but there are essentially two types of weather maps. There are maps or depictions of what is occurring at the surface. And there are maps and depictions of what is occurring in the upper part of the atmosphere. Okay, and they're actually have two different purposes. The weather maps at the surface are a depiction of what is happening, right? So it's letting us know exactly what the weather we're experiencing on the ground is. The weather maps of the upper levels of the atmosphere give us more a depiction of why. So the stuff that is going on basically in the middle and upper parts of the atmosphere are controlling the weather at the surface. So we use the maps in the middle and the upper parts of the atmosphere to help us understand why the weather at the surface is occurring. Okay, and so we actually went over this part of it, right, and how to read. And these are surface weather depictions, so we went over how to read this already. But there are a few other things that you might see on a weather map that I want you to also understand. And so there's these L's and H's. L's depict areas of low pressure at the surface. H's depict areas of high pressure at the surface. And some of the other things that I want you to know are, I basically want you to know these two guys. The blue lines with the barbs is a cold front. The red lines with the pips are essentially a warm front. So what does this mean? So for instance, if you look at this symbol, what this means is that cold air is traveling in the direction of the pips. So cold air is traveling essentially, in this case, would be from southwest to northeast. So we're actually tracking the movement of cold air. All right, so these depictions, these cold fronts and warm fronts, are boundaries between warm and cold air masses. And if you see a cold front, that means that cold air is overtaking warm air. And if you see a warm front, that means that warm air is overtaking cold air. So in this case, the warm air is moving from the southwest to the northeast, again, in the direction of the pips. So for instance, if we look at sort of this map here, and you see this cold front, what this tells us is that cold air is actually spreading towards the southeastern part of the United States, right? And so if we were in Miami, Florida, for instance, down here, we might expect that the temperature over time is going to decrease because the cold front is moving in our direction, which means that cold air is overtaking the warm air. Now, another thing that you'll see on a weather map is isobars. What isobars are basically just lines connecting points where the pressure at the surface is equal. So for instance, you see up here in our little depiction, the line is actually connecting. You notice that the line is actually connecting on the bottom line is connecting everywhere where the pressure is 1,000 hectopascals or 1,000 millibars. The top line is connecting all of the points where the pressure is 996 millibars. So basically, the isobars give us an idea of what the distribution of pressure is at the surface. And we could actually kind of try to create our own isobars by looking at this pressure map at the bottom. So this is basically the pressure at different locations. And so if I wanted to draw isobars, say, every 5 millibars, I might say, okay, well, I have 1,005 over here. 1,010 would go something like this, right? Because it's going to be close to this. 1,015 might look something like this. 1,020 might look something like that. And so we can actually sort of surmise what the pressure field looks like. And the reason that we care what the pressure field looks like is because this determines what the wind field does. So when we look at maps, the winds will actually tend to blow counterclockwise around low pressure systems and clockwise around highs. Okay, and the wind is actually parallel to the isobars. So for instance, the winds would actually be blowing in this direction for this depiction up here. Okay, and the idea is that it goes basically with low pressure to the left of the wind. Okay, so you'll notice that my wind direction is pointing in this direction. That means that the low pressure is to the left. And so how do you visualize this? What do I mean when I say to the left of motion? Imagine that you're in a car and you're driving in a direction. The left-hand side of the car is to your left, right? So if your car was following the wind, the area where the pressure is lower is to your north, which in this case, if your car is traveling from west to east, north is to your left. Right, so it's on the left-hand side of the car. If you make a left-hand turn, you would actually move towards lower pressure. And so the shape of the isobars tells us which direction the wind is blowing in. The number of isobars, or how closely spaced the isobars are, tells us how strongly the wind is blowing. The closer the isobars are together, the stronger the wind. And so if we were to look at, say, a map at the top there of what the winds were looking like, without knowing anything else, I could immediately tell you that there was a low pressure system somewhere in here. And why do I know that there's a low pressure system somewhere in there? Because the winds around it are generally blowing in a counterclockwise fashion. So the fact that the winds themselves are actually turning in a counterclockwise fashion, so you see that the winds, for instance, here are coming from the south, here they're coming from the northeast, here they're coming from the north. And so the fact that the winds are actually circulating in a counterclockwise fashion tells me that I have a low pressure system there. And when we depict that in terms of isobars, that would end up looking something like this. So these maps are essentially from the same time. Right? One is just the actual surface observations, and the other is basically a depiction of the isobars associated with those surface observations. Now, because of the fact that the winds tend to blow counterclockwise around low pressure systems and clockwise around high pressure systems, it also ends up telling us something about what kind of temperatures we might expect. So here's a low pressure system. We know that the circulation around the low pressure system is counterclockwise. So we know that to the east of our low, things are blowing from south to north, and to the west of our low, things are actually blowing from north to south. So we tend to have warmer temperatures on the east side of our low because the wind is actually blowing from south to north. And so it's actually drawing warmer air from lower latitudes northward. And it actually draws cold air on the west side of the low pressure system. It draws cold air from north to south. So the circulation around a low pressure system actually ends up sort of dictating that our warm fronts and cold fronts kind of always look like this around our low pressure systems. So we will always see warm fronts essentially extending eastward from our low pressure systems, and we will always see cold fronts extending westward and southward from our low pressure systems. And so if I look at a map of temperatures, everybody see basically that it's warm here and cold here. All right, so the temperatures are essentially warmer to the east and colder to the west. Just by looking at this map of temperatures, if I knew nothing else, I would know that there is a low pressure system sitting somewhere here in between these, because I know that to the east of the low pressure system, the winds are coming from the south. And so I know that the warm plume has to be where the winds are coming from the south. And I know that the cold air has to be where the winds are coming from the north. So I can actually position my low either by looking at the winds or often by just looking at the temperature fields associated with them. And we can kind of get the same information from the dew points. The warmer air tends to be more moist, and the colder air tends to be drier. Okay, actually, I'm not going to harp too much on these next couple of maps. I want to switch to upper air maps. So those are the surface maps, which are basically telling us what is happening. Now we're switching to the upper air maps that are telling us why things are happening. Now, one of the things that you have to remember when we talk about upper air maps is that in the upper levels of the atmosphere, and I can't stress this enough, that it's the upper levels of the atmosphere, there's a one-to-one correlation between temperature and pressure. All right? So this is a cross section, right? So we have altitude going up here, and then let's just pretend that this is the bottom of the box is going from west to east, okay? If the temperature is the same everywhere, that means that the thickness of the atmosphere is the same everywhere. And if we were to plot the pressure at 3,000 meters and up in the atmosphere, everywhere the pressure would have the same number. It would be 700 hectopascals everywhere at 3,000 meters. If there's no pressure difference, there's no wind. Okay? But as soon as we introduce a temperature gradient so that where it's warm, the atmosphere is thick, and where it's cold, the atmosphere is thin, that means that this 700 hectopascal surface becomes sloped. Okay, so now, if we choose to look at 3,000 meters, and we go from where it's warm, the pressure here is going to be high. It's going to be higher than 700 hectopascals because we're actually closer to the surface, right? And as we go closer to the surface, the pressure always has to increase. So as we move down, the pressure will go up. Whereas at 3,000 meters over here, the 700 hectopascal surface is below us, which means that the pressure is low. So at a level, at 3,000 meters, we're actually going from high pressure to the west to low pressure to the east, which is the same as saying that we're going from where it is warm to where it is cold. Those two things are equivalent statements. Now I'm going to do something that might get a little more confusing. So in meteorology, we tend, in the upper air, we tend not to plot maps of pressure at a constant height. So in other words, when we look at a weather map in the upper levels of the atmosphere, we are not actually plotting what the pressure is at 3,000 meters everywhere. We are not plotting what the pressure is at 5,000 meters everywhere. We do not do that. What we actually plot is what is the height of the pressure surface. So what is the height of the 700 hectopascal surface? So for instance, if we were looking at a weather map in the upper levels of the atmosphere, what we would see is a number of 3,200 meters at that westward location for the height of the 700 hectopascal surface. And we would see a height of 2,800 meters at our east location. And so the take-home point is that the depiction of height on a constant pressure surface is exactly the same as the depiction of pressure on a constant height surface. We're still moving from high pressure to the west, low pressure to the east in this picture, or high heights to the west, low heights to the east. So we can use heights on a constant pressure surface or pressures on a constant height surface interchangeably. And you may be asking yourself, why would we complicate things like that? Like, why would we choose to plot the heights on a pressure surface? It's actually because our equations are a lot easier to deal with when we plot things on a constant pressure surface, right? So this is a mathematical convenience for meteorologists. And so these two maps of pressures, so the bottom map is actually pressures at a constant height. The top map is heights at a constant pressure, right? So you'll notice that the units in the top one are meters, the units in the bottom one are hectopascals, and you'll notice that the patterns are exactly the same. Makes no difference. And so we can use the same rules that we used for winds blowing counterclockwise around low pressure systems, clockwise around high pressure systems. We can use those rules to actually let us know that the winds are blowing something like that, right? Because the pressures are lowest in the center there, and they're higher on either side. And so, again, low pressure wind blows with low pressure to the left, high pressure to the right. And remember that the wind follows the isobars, or the height lines. So the wind will always tend to be parallel to the height lines, or the pressure lines. And so I think actually I end with this. So this is a depiction of heights at 300 hectopascals. So what this is telling you, for instance, is that you have to go 8,820 meters up in the atmosphere at that point to get to 300 hectopascals, okay? And so we see that the heights are low here, they're high here, and we can see that the wind is blowing counterclockwise around our low and then turning clockwise around our high. Again, it will always be with high pressure to the right, low pressure to the left of the wind. And you can actually see the wind directions. And just by seeing this depiction of pressure or heights, you also know that it's cold up here, and you know that it's warm down here. Right? All you would need is the depiction of heights, or the depiction of pressure. You would know which way the winds are blowing. You would know where on your map it is warm and where on your map it is cold, by just correlating those two things. Okay, are there any questions on this? Okay, so we'll end it there for today. The next couple of classes will actually be, I'm at a conference in Seattle, but I have a very trusted person coming in to cover the next couple of classes, Georgina Paul. She's actually really cool. You might actually like her better than me. So if you do, keep it to yourself.